Okay, so I can see it's working. I'm Miss Drury. I'm from Williamwood High School, and we're going to be trying to get through 2 topics today, which is pretty crazy. So let me get this started. All right, so first we're going to go through organic chemistry, and then in the second half hour we'll go through nuclear, and I'm going to do the best I can to get through both topics in 1 hour, unlike the other sections where there were one topic per hour. So we're going to go kind of quick. Organic molecules must have the carbon in it. Hydrocarbons have both hydrogen and carbon. Therefore, hydrocarbons are organic, but all organic compounds are hydrocarbons. So CH4 is a hydrocarbon and is organic. CCl4 would be an organic substance because of the carbon, but not a hydrocarbon. And then oxygen, a lot of people for some reason think is a hydrocarbon and organic, but it's neither because it does not have carbon, and a hydrocarbon because it doesn't have hydrogen or carbon. These things are found in fossil fuels, plants, and animals, and examples include gasoline, oil, kerosene, butane, propane, and I'm sure you've heard of these things before. Hydrocarbon properties are mostly insoluble if they're nonpolar. There are some exceptions we'll go through later. And most of them are non-electrolytes, meaning they cannot conduct electricity. There is one exception in our table R called acids, which you probably previously covered and we'll review again later. They react very slowly because they're covalent and nonmetals only. And as their size increases, their melting point and boiling point increases because they have stronger forces. Smaller hydrocarbons may be gases, and larger hydrocarbons may be solids at room temperature because the higher their mass, the stronger their forces. Remember that carbon has 4 valence electrons, therefore carbon will bond 4 times to achieve an octet. So this is what our simplest hydrocarbon will look like, methane. Each of the dot represents a valence electron that carbon and hydrogen added to the bond to form 4 nonpolar covalent bonds. Each of those bonds is 2 electrons, 1 from the carbon and 1 from the hydrogen. Sometimes double and triple bonds might be needed to fulfill the octets, so you'll see things like ethene, the double bond sharing 4 electrons, or ethine, a triple bond sharing 6 electrons. Notice that when I mentioned those, their names ended differently, ethene and ethine, telling you what kind of bonds you have between the carbons. So just backing up, all single bonded hydrocarbons are in the same family known as alkenes, and all double bonded ones are in the same family known as alkenes, and triple bonded would be hydrocarbons that are alkynes. So you can refer to table Q to figure this out, which we can see here. Alkanes always have single bonds, enes with double, and ines with triple. You can see the name of a substance that has single bonds also ends in ane, just like the family name, and ene for alkenes and yne for alkynes. And they have a specific general formula. Some students choose to ignore the general formula and they'll just draw out their structural formula and then figure out how many hydrogens they have by just counting. Other students will follow the formula because they're good at math and they will not need to draw it out to figure out how many hydrogens they have. So for example, in the alkane section, what I say is if you have only 1 carbon, to figure out how many hydrogens you have, you could draw it out, or you can do 2 times the number of carbons, 1 plus 2, and so that means you have 4 hydrogens. In the example they gave you, there's 2 carbons, so 2 times 2 is 4 plus 2 is 6 hydrogens, which you can figure out either by drawing or counting or by the formula. Alkenes are exactly double, so however many carbons you have exactly double the number of carbons and hydrogens, so C2H4 is shown in the example. And alkynes have even less hydrogens, so you can see every time you add a bond on between the carbons, your number of hydrogens are decreasing. And that's something called saturation. So the first alkane group are all saturated because they're saturated with hydrogens, there's just so many hydrogens. Whereas alkenes and alkynes have less hydrogens, and therefore they're unsaturated. So again, the picture shows you the number of bonds, and table Q also tells you how to calculate those bonds. Table P tells you the prefix. So in the examples that we saw, they were eths, and I mentioned some meth groups, and it's just telling you how many carbons you have. The more carbons you have, the more hydrogens you'll have as well. So we have prop, bute, pent, hex, hept, act, known, and dec. all can be copied from table P, and you're just counting how many carbons only to figure out your prefix. So putting that together, we should be able to name any hydrocarbon given the prefix and the suffix. The prefix being how many carbons you have, the suffix telling you if you have single, double, or triple bonds, either by drawing it out or by using the formula on table Q. So the first problem, I'm assuming it's an F group because we have 2 carbons, and since the hydrogens are more than double, it would be ethane. I guess I'm just going through the prefixes here. So 2 is prop for 3 carbons, 4 is bute, 5 is number 4 is pent because of the 5 carbons, and you can see them, I just kind of put them in order. But all we're looking at is how many carbons they have. If you want to go through the suffix now, you would have to figure out the ratio of hydrogen to carbon. So putting those together, you can name these simple hydrocarbons. The first one has 1 carbon, so it's meth. And since they're single bonded, well, carbons are not bonded to each other, it's ane. In the second example, going to the right, there's 2 carbons, so it's F. And since there's a double bond, it's ene. In the third example, on the bottom left, you have 4 carbons, so it's bute. And since they're single bonded, ane. And the last example, because there's 2 carbons, it's eth again. But because it's a triple bond, it's ene. Pretty straightforward, I feel. As I mentioned before, compounds like fats that are saturated would have a lot of hydrogen, and this requires single bonds. Alkanes that are saturated have single bonds. Compounds that are unsaturated have double and triple bonds, therefore they have less hydrogen atoms because they're using some of their bonds for carbons instead, so alkenes and alkynes are unsaturated. There's a special type of hydrocarbon that they come up on the test every now and then and you just need to memorize. It's called benzene. They say it's an aromatic hydrocarbon in that it smells really good. It gives you an aroma, so this comes up in things like cinnamon and vanilla. Basically, at each corner that you see on my hexagon, there's a carbon, and so that means there are 6 corners or 6 carbons, so C6, and then they're all connected by either a single or a double bond alternating. The double bond can be on the top, side, or it can be on the 3 other sides. It doesn't matter how you want to draw that, it just has to be alternating. And because carbon bonds 4 times, you can see in the corner, the carbon is on a double bond and a single bond. That means there's an imaginary hydrogen there. So for every carbon there's an imaginary hydrogen. The formula for benzene is C6H6. So you need to memorize how it looks and the formula. There's also these fancy branched hydrocarbons that we need to talk about. When you're naming the branched hydrocarbons, you're going to name the longest chain and use that as its last name because it's the most important part of the name, just like your name. Then you're going to name the shorter chain specifying the position on each branch. And make sure your branches are numbered as low as possible. So for in this example, the longest carbon chain, the most important one, is the one that's numbered here, 1, 2, 3, 4, 5, 6, 7. So that's 7 carbons would be hept. I picked that particular carbon going up because it had a double bond. And that's the more important part of the chain, so heptene. The ene is on the first carbon, so its last name is 1-heptene. Now, if you notice, there are 2 other carbons hanging off the third carbon. Those are going to get a new smaller name as your first name. So 2 carbons would be eth, they're single bonded, so ane, but they always will be. But whenever we have these hanging carbons, we want to give them a cute little name. So instead of ending it in ane, we're going to change it to il, YL. So this is going to be ethyl on the third carbon, so 3-ethyl, 1-heptene. Let's do that a few more times, but before we do, just so you know, they might try to trick you. All of these are actually butane. So just because it's bent does not mean that it's not in a chain. These are all connected, so essentially I could straighten them out and they'd still be connected. And so they're not any of these branches. The branches always start on the second or third carbon. So here's another example of a branched hydrocarbon. This one, you can see that there are 3 carbons in a row, so it's prop. They're single bonded, so ane. And then there's a little methyl group hanging down. So on the second carbon, 2-methylpropane. Another example, finding longest carbon chain would be going across 1, 2, 3, 4, 5, 6 carbons, all single bonded. So hexane is its last name. And again, a methyl group hanging on the second carbon, so 2-methylhexane. The most common branched ones are just methyl groups hanging on either the second, third, or fourth carbon. So remember to end them with YL. Maybe they get real fancy and they'll have 2 methyl groups. In this case, again, name your longest chain, which would be 1, 2, 3, 4, 5, 6 carbons in a row again, and they're all single bonded, so hexane. And then tell me about the methyls. The methyls happens to be on the second carbon, and then if you keep counting from the left side, it looks like the 5th carbon. So this is 2,5-dimethylhexane. I know it sounds redundant, but we mentioned that where their placement is 2 and 5, and that there are 2 dimethyl. Again, find the longest continuous chain of carbons. This is the parent chain, and look at all the bonds between the carbons determined to type of hydrocarbon. In this case, we're going to count from the side that has the alkyl group. So count from the right because that makes our numbers lower. We're going to count how many carbons there are. So there are 7 carbons. And so that means our last name is heptane. And then we're going to count the little chains hanging down. So these are the alkyl groups starting with the smallest number. So we're actually going to number it, as you can see, if you counted from the left to the right, it would have been 4, 5, 6. But we're going to count from the right, 2, 3, 4. That's way better. And so our prefixes are in the 2nd and the 3rd and the 4th. The 2nd and the 3rd are both methyl, and the 4th is an ethyl group. So that means we're going to say there's 2 methyl groups on the 3rd and the 4th, and a 2nd and a 3rd, sorry, and then there's a 4th on the ethyl. If you ever see prefixes, di just means there are 2 times, tri means there's 3 times, 4 times would have been tetra, and 5 is penta. That's getting a little crazy. You probably only see dis and tris. So the name of this altogether would be 2,3-dimethyl 4-ethylheptane. I really don't expect to see anything that hard, but if you could follow me through this, you're probably fine. There are other groups that can hang from your carbon chain, such as fluorine, chlorine, bromine, and iodine. Instead of calling them that, we're going to call them fluoro, chloro, bromo, and iodo. They're underneath the halide section of your reference table R. So for example, this one, every time you see a little carbon corner, there's a carbon. So I would say that there's 1, 2, 3, 4 carbons in a row. Every time you see that corner, remember to count it. So butane. There's a bromine on the 2nd carbon and a methyl group on the 3rd carbon. So 2 bromo, 3 methyl butane. Here's another better example. 3 carbons in a row would be prop. Single bonds are ane. There's a bromine on the 2nd carbon and a methyl on the 2nd carbon. So 2 bromo, 2 methyl, propane. Here's something I don't expect to see, but you can follow along with me to understand what's going on. This is a benzene ring, so I wanted to make sure we remembered that. And on the benzene ring, there's a bromine and a methyl group, and they're really far away, so bromine might be on the 1st, and methyl would be 2, 3, 4 spots away, 1 bromo, 4 methyl benzene. There are 3 types of formulas we're kind of mixing here. A molecular formula in which you tell me how many carbons and hydrogens there are total. A structural formula in which you draw it out. And a condensed structural formula, which we'll be seeing on table R, where you say, after you've drawn it out, the carbon and how many hydrogens are connected to it in order, a carbon and how many hydrogens. So the most common of the first 2, condensed structural formulas really only show up on table R. Isomers are 2 substances that have the same molecular formula. So if you go back, again, the number of C's and H's written out are the same, but their structure is a little different. So again, when you draw it out, it'll look a little different. So 3 isomers butene might be like 1 butene, where it's in the same number of C's and H's, so C4H8, but the double bonds in the first set of carbons. Or 2 butene, where again, you have C4H8, but the double bonds between the second 2 carbons, so 2 butene. These 2 substances will have the same molecular formula and the same different structural formula. So its percents might be the same and its mass might be the same, but their properties are slightly different. How they bond is different, so their properties are different. I can even make something real crazy like cyclobutane, but that's not tested, so don't worry about anything in a cycle. Why not 3-butene? Now, if you try to put that double bond on the 3rd chain, you're really redrawing 1 butene. So remember, again, that your double bond has to be on the side that's, numbered 1. So let's see if we can find any isomers in here. Again, an isomer is something that has the same number of C's and H's, so what I would do is count them up. The first one has 4 C's and 10 H's. The next one to the right has 4 C's and 10 H's again. So those might be isomers in that they have the same number of carbons and hydrogens, but they're aligned a little differently. On the bottom, we have 5 C's and 12 H's, so that cannot be circled in purple. The next example over, again, 5 C's and 12 H's, so those 2 are similar. And the last example, 5 C's and 12 H's, so those are all isomers. So you can see how isomers will have the same numbers of C's and H's, but in a different alignment. At this point, I want to taught you to take out table R. so you can look at some of the weirdos that you're going to see on the test. Basically, the reference table gives you the answers in this section, which is pretty nice. So as we mentioned before, halides, they're telling you what you're going to write, fluoro, chloro, bromo, ido. You just need to tell me where they are, and they give you an example. So an example they gave you, I remember that they said that this is condensed. I recommend drawing it out. So that means the first carbon has 3 H's drawn on it, the second carbon has 1 H drawn on it, and a chlorine drawn on it, and the last one has a C with 3 H's. That means we have a total of 3 carbons, so prop. They are single bonded if you draw it out, so ane, and there's a chlorine on the second carbon, 2-chloropropane. The one that I drew has 2 carbons, and there are 2 bromines. The bromines on the first and the second carbon, so I would say something like 1,2-dibromo ethane. Alcohols are anything that ends in OH. The OH can be on the last carbon, which most likely it will be, but it can also be in the middle carbon. So we talk about where that OH falls. An example that they have in your reference table looks like this. There are 3 carbons in a row, so prop. They're single bonded, so ane. But instead of ending in ane, because that would be propane, they put an OL ending for alcohol. The alcohol group is on the first carbon, because remember again, you want to number your functional group or your weird parts as low as possible. So we don't want to say it's the 3-propanol, we want to say it's the first carbon, and always count from the right side for this example. So this is what it looks like drawn out. I could also put that OH on the left side, and that would still be 1-propanol. It's almost like these molecules are twisting in space, and so you can see them as the way I drew it, or a reflection in space with the hydroxide on the left side. So all alcohols will have a suffix OL. You can have things like methanol, ethanol, propanol, butanol, and I can go crazy. So you're just changing your number of carbons. Important parts about alcohols is that they're flammable. So you might have seen demonstrations or videos whether you can set alcohols on fire, and that they're soluble. So you probably know that the alcohol that we use to treat infections and wounds, or that some adults use to drink, are not pure alcohol, because you would die from that. They are mixed with water and you can't even see, so they're a homogeneous solution. And they're soluble because of that OH bond. If you remember from watching some of the videos earlier today, that OH bond is a polar bond, and so it's much like water that has polar bonds, so they're dissolved in each other. Ethers look similar to the alcohols, except for it's not going to end in H. So the alcohol is a single bonded O connected to an H. An ether is a single bonded O connected to another set of carbons. So it doesn't end the chain. In this example that they gave you in your your reference table, there's a carbon with 3 H's connected to an O that's connected to 2 other C's. So we're going to name the 2 chains separately. There's a methyl group, an O, and then an ethyl group, so methyl, ethyl, ether. They end in ether, just like the example that they give you. You can have any mix of this, like methyl, methyl ether, ethyl, ethyl ether, ethyl, propyl ether. Whatever you count as your carbons is the prefix you'll use, and you just end it in ether. Most chemists name the small chain first, then the large chain, and then end in an ether. Important things about ether is that they're anesthetic, and if the O is close to the end of a chain, it could be soluble. Anesthetic means it puts you to sleep so we can do surgery. The thing is, we don't really use it anymore because it also makes you sick. Aldehydes. You might have heard of formaldehyde used to preserve specimens, thus the picture of the brain on the side. Aldehydes have a double bonded O, so you can right now tell the difference between this and an alcohol and ether, because it has a double bonded O. We say this is at the end of the chain, so the double bonded O is connected to the carbon, and that carbon is connected to just a hydrogen, no more carbons. So it's at the end of the chain. You can also see with the R here. The R just means that there's more carbons, any amount you want. So the example they gave you is propanol, which can be drawn like this. There's a carbon connected to 3 H's, another carbon connected to 2 H's, and then your functional group. So because there's 3 carbons in a row, you have prop. And because there's a double bonded O at the end, it's an aldehyde, so Al. Make sure that A looks like an A, not an O. An O would be alcohol, right? You don't need to tell me what number it's on, because the aldehyde has to have the functional group at the end, so it has to be number 1. If you gave it, it wouldn't be at the end of the world, but if you gave it to me as a 2, 3, 4, 5, or anything else, it would be wrong. So again, a suffix of an Al. They can be soluble if the O is at the end of a chain, and they can be very reactive or preserving specimens. Ketones look really similar. So if you go back, aldehyde has a double bond O at the end. ketone has it somewhere in the middle of the chain. So if you see the picture I have, show them bent up, but it really would be 5 carbons in a row. That's the pent. And then the one is talking about the double bonded O in the middle. It could be anywhere in the middle. That's in the 2 or the 3 section. So we're saying it's specifically on the 2 carbon. You will not see ketones that have a prefix of 1, because that would be an aldehyde again. The most common ketone that you're probably used to is acetone, which is used in nail polish remover. Notice the ONE ending. And it could be somewhat soluble, like the acetone that you use in your nail polish. They need at least 3 carbons so that the double bond O is in the center of the chain. Again, you can have propanone or butanone or pentanone. You're just counting how many carbons it is and where is that double bond. Acids are different, again, because they have a double bonded O and a single bonded O at the end of a chain. So if you look at the example they have, propanoic acid has 3 carbons in a row, thus the prop, and then we ended in anoic acid. AN for the single bonds and oic for the acid. You can have, again, methanoic, ethanoic, propanoic, butanoic, just count your carbons and end it in an oic acid. Some other important things is, again, you don't have any numbers because it has to be at the end of the chain. And they're weak electrolytes, as I mentioned in the beginning, meaning that they can conduct electricity, but these acids are so weak that they conduct very weakly and they probably won't really hurt you too much. But they can conduct electricity, so it is important. Something very similar is an ester. Notice the relationship, organic acid, double bond O, single bond O. So does an ester, double bond, single bond. But the organic's at the end, and the ester is somewhere in the middle. So again, you have this relationship like an ether, where you have to tell me both carbon chains. In this case, we do not go from small to big. We go from the part of the chain that's the least important first, and then the last name, just like we talked about earlier in the session, the last name is the most important name. So your functional group needs to be part of the last name. So in this example, the functional group is on the prop part, the 3 carbons. So propanoate is your ending, and methyl is just the less important part of the group at the beginning. So again, name the chain adjacent to the double bonded O, last, and the suffix is ananoate. So they smell great. Their perfumes and foods have them, all fruits, and so we really like esters. Amines means there's a nitrogen present on the chain. The example that they gave you was 1-propanamine. That means there's 3 carbons, and NH2 is at the end on the first carbon. It could be in the second and the third carbons as well, so you need to tell me where the nitrogen is present. You can also use it as a prefix, like amino. So this might be published somewhere else as a amino group on the propane, but I wouldn't worry about that too much. It's basic and it's used in dyes and found in the proteins like amino acids. And then amine, here you have an amino acid with the amino group and the acid group together. Thus why it comes up. Last, amides on your list means it has an amine group, but it also has the oxide group. So they kind of just smush them together and make amide. The example they give you is propanamide, meaning there are 3 carbons in a row with your functional group at the end, the double bonded O and the N. So amide would be your suffix, and again, it's used in dyes. If I can go back just for a second, I wanted to mention that if you notice, there's a little bit of a flow to your table R. So after halides, you have alcohol, starts with an A, then ether that does not. Aldehyde starts with an A, then ketone that does not. Then acid that starts with an A, I know it says organic, but acid starts with an A, and ester that does not. The reason I bring this up is if you go through all the A examples, such as alcohol, aldehyde, and acid, all these have their functional group at the end of the molecule. So an alcohol, OH at the end. Aldehyde, CO at the end. And last, acid, COOH at the end. That's how some people remember it, that the A's have their functional group at the end, whereas anything else like ester, ether, and ketone, their functional group's in the middle, and you have to tell me where in the middle it is. So it's just a little way of helping you remember to put your 1s, 2s, and 3s at the beginning. All right, polymers are long chain carbons. So they'll take smaller chains like C2H4 and they'll link them together, almost like linking paper clips together. And so the little N at the end is just saying it could be like 100 of these linked together. I don't know. We can use them in plastics, rubber, and nylons, and basically very important. So polymers have that little N or a little X at the end. Now for organic reactions. This is not on your reference table. So out of everything we just talked about, everything's on the reference table except for this. So this is something that you're going to definitely want to review. An addition reaction is one where you literally add two things together to form one thing. It's like synthesis, but it's carbon-based, right? And just like math class, you start with two numbers, like 2 plus 3, and you add them together and you make one number, 5. That's happening in our reaction. So in our reaction, I have an example of C2H4 is one compound, bromine's an element, and we're adding them together literally to make one product, C2H4Br2, right? Notice the first compound is unsaturated, so you have to break the bond open. If you drew it out, there's a double bond. You're breaking it open to allow you to add in bromines, right? So you can imagine that in your head, hopefully, or in a lab that you might have done. You break open the double bond and you add in the bromines. So all additions are unsaturated before you have the double bond and after you don't. Substitution looks really similar, but you're switching your atoms. So it's still going to be a hydrocarbon that's getting some kind of bromine or fluorine or iodine, but you're switching their places with a hydrogen. So this is more like single replacement. You have two reactants and two products. The CH4 is saturated. So in order for you to have a substitution, I always remember the S rule. You have a saturated, single bonded hydrocarbon that undergoes substitution. So before you have single bonds and after you have single bonds, nothing has changed. You just took off an H and you added in a bromine. Well, you switched with a bromine, I should say switched. So substitute switches, saturated, single bonds. Combustion means you're burning in an oxygen. I know that you probably talked about this earlier today. So you add an oxygen, and whatever substance you started with, all those little elements get oxygens on it. So the carbon gets an oxygen, gets CO2. H gets some more oxygens, you get H2O. Esterification means you're forming an ester. Surprise! So your product has to have an ester in it. And if you go back to table R, an ester is COOC. So you can see that at the end. In the beginning, I'm starting with an acid and an alcohol. The alcohol and the acid are dehydrated, means you take out the water. The OH of the alcohol smushes with the H of the acid. That makes the water at the end of your reaction. And then those live bonds that are no longer bonded to the O's and the H's smush together, and you form the bottom. So you form this ester, and then it has a single bonded O and a double bonded O in the middle of your chain. Water is left over, that's important. Most likely, the type of questions you'll see are just you identifying that an ester is formed or knowing that an acid and alcohol makes the ester. Fermentation forms an alcohol. Again, the only thing you really need to memorize is that it forms an alcohol because table R shows you what an alcohol is, OH. This is the exact equation they use every single year. So they're showing you sugar breaking down into an alcohol and CO2. And then saponification, the only thing you need to know about it is it makes a soap. You don't need to know any of these fancy formulas or anything. But if you want to know the background, basically we're taking a base and we're adding it to a fat. And the fatty molecule creates that soap. Addition polymerization, if you remember, a polymer is a long carbon chain, and the only way you can make that long carbon chain happen is to take your double bond and open it up and allow them to link up. So like I said before, it's kind of like taking a bunch of paper clips, opening them up, and then linking them together. So they were all separate monomers, and they're now connecting to form polymers. Another way of doing that is to dehydrate it, like we saw in esterification. So you could take the OH of one side and the H of another, take them out, make water, and then connect the live bonds together. Either way, what you really just need to know is polymerization means you're taking small chains and making them really long. Cracking is the opposite. You're taking a really long chain and you're breaking it down. This is how we create, when we drill for fossil fuels, how we create the propane separate from the butane and so on. So we just heat it up, they crack, and then we distill them into their separate areas. Whew, that was a lot of organic chemistry. So I thought I had some examples, and they seem to have disappeared on me. Let's see if they're somewhere. I had examples from the recent exam. There they are. I wonder how that happened. All right, so the June 2015 exam has some, I felt like you can find these examples anywhere, but I just wanted to go through the recent exam. Hydrocarbons are composed of elements of, hopefully you picked hydrogen and carbon only. And 18, which atom is bonded to a carbon atom in a functional group of a ketone? So you're going to look at your ketone and see that it has a double bonded O in the middle of the chain, so I'm going to pick oxygen. Also in that exam, we have number 19, two types of organic reactions are, and if you go through the examples, number 1, sublimation is solid to gas, so that's not even an organic reaction. Number 2, deposition is going from a gas to a solid, so that's not an organic reaction. Number 3 says decomposition, nope. And evaporation, nope. And number 4, esterification forms an ester, and polymerization makes a polymer, that's what I would pick. And then number 20, isomers of butane and methyl propane have, well, if they're isomers, something has to be the same because that's what iso means. So they're going to have the same molecular formula, but because they're arranged differently, they'll have different properties. Answer 2. And number 48 on the exam, they have this big, beautiful graph, and it says, what is represented by the number 1 and the IUPAC name for these alcohols? And as you can see, methanol, ethanol don't have it, but 1 propanol, 1 butanol, and 1 pentanol does. And so the number 1 tells you not how many hydroxides, but the location of the hydroxyl group at the end of the carbon chain. So that's answer 3. If they were in the middle, it would have a 2, 3, or 4, and so on. Okay, now we're ready for nuclear chemistry. We're going to be talking about radioactive isotopes. Completely big change. So just to review from some previous stuff you talked about today, isotopes of an element have the same number of protons, but a different number of neutrons, which results in a different mass. So if you wrote the isotopic notation of C12 and C14, they would look like this. They're the same exact element, and the protons are the same, so you're getting the same formula symbols, except for their masses are different, so that top number is a little different. So what makes an isotope radioactive? And that just means it's decaying and it's unstable for some reason. Most likely it's unstable and decaying because their protons are not equal to the neutrons or not even close. Or it could be decaying because the atom itself is just way too big. You don't really need to know why it decays, you just need to know that it can. Certain isotopes do. And which elements on the periodic table have no stable isotopes? Anything uranium and later. So number 92 and on are all just too big to stay stable. They just have too much going on in their nucleus, and so they're radioactive. Again, you're going to see isotopic notation looking like this. These reactions look nothing like any of the reactions you've seen all day. Because of this isotopic notation, you want to show what's happening to both protons and neutrons. If you subtract them, you can figure out how many neutrons it has. So radioactive decay is when your nuclei emits particles and changes it into a new element. Never ever have you seen this except for this unit. Otherwise, chemical reactions, you keep the same chemistry going on the whole time. The elements stay the same. This is the only unit that you're going to see elements change and morph into another element. And honestly, the Regents exam has always had this be its last topic. So you'll see questions about this. Is either question number 24 and 25 at the end of part A, or 49 and 50 at the end of part B, or somewhere at the end of part 2s. So you shouldn't be seeing elements switching to other elements until the end of a part of your exam. So again, this rule still holds. You cannot change an element's number of protons because it would change its identity. And that's exactly what we're going to be doing here, and that's why our reactions look different. So basically, scientists put together a chart, and they found all the stable isotopes, and you can see them right here, what we call the band of stability. Nothing that you really need to know, just a helpful way of explaining why some things are not stable. And that's due to their proton-neutron ratio. So basically what they're saying is if it was a 1-to-1 ratio, they would fall on the red line that you see. But as there's more protons, they needed more neutrons to almost serve as bodyguards, because the protons hate each other, they're both positive, and the neutrons kind of go in between the protons to make them stop repelling each other as much. And so the more protons you have, the more bodyguard neutrons you need. And so that's what makes them really stable. If, at any reason, you fall higher than that band of stability, what that's saying is you just have too many neutrons, and so you're going to release a beta particle. Do you need to memorize this? No. What you can do is just go to your tables, and it tells you if it's going to beta decay. it also tells you on tables N and O if it's going to beta decay and what a beta particle is. You can write the beta particle as 0 minus 1b or 0 minus 1e, whatever you feel more comfortable with. I like the E because it means electron, but some people like the B for beta, so it's up to you how you like it. The reactions that you might see that release beta particles include iodine, is probably the most common one. Iodine is common because they sometimes ask you what it's used for, and it's used to treat thyroid problems. I remember iodine, thyroid, they kind of go together, right? And so basically a person will take an iodine capsule and the iodine will flare up on your thyroid if you're having thyroid issues. Anyway, moving on. You would show the iodine that is radioactive, and then you show after the arrow your particle that's going to be emitted because it's radioactive, the beta, and you figure out what's left over. So if you notice that beta does not affect its mass at all, the 131 sticks, but the protons have changed. What you normally had as 53 protons is now switching over and forming 54 protons, and that changed the identity of iodine to xenon. I always treat the arrow sign as an equal sign. So on the bottom, basically, it's saying 53 is equal to minus 1 plus 54. You can also for under the band of stability. In that case, you're going to form a positron. Do you need to memorize that? No. What you can do is use tables N and O, again, to see that which type of things might positron decay and what a positron is. So again, I like to show a positron as 0 plus 1e because it's like electron, but other students might like the little b. It's up to you, whatever floats your boat. But your reactions will, again, have that positron after the arrow, and you'll have to figure out what's left over. So again, with a positron, it does not affect the mass, so the mass stays exactly the same, 11, 11. But it does affect the protons. What you usually have as 6 is now gone, and now you have 5 that change the identity to boron. Again, the arrow acts like an equal sign, so on the bottom you have 6 equals 1 plus 5. That's how I know I'm right. Some substances just alpha decay because they're humongous. Do you need to memorize that? No. Tables N and O tell you which one's alpha decay and what an alpha particle is. I like to write alpha particles as 4 over 2 He because 2 means it's helium. Other students like to write it as 4 over 2 alpha because they like the squiggly A. It is whatever you want to write. That's fine. You just need to make sure you get the right product and that you write your alpha particle after the arrow, not before. So again, if you want to figure out what's left over, the arrow acts like an equal sign. So on the top, I have 234. The alpha particle releases 4 masses, and so you're left with 234. On the bottom, you had 92 protons. The alpha particle releases 2 protons, and so at the end, thorium is number 90. Thus, its identity has changed. Alpha particles are humongous, right? Compared to the beta particle that had no mass and the positron that had no mass, alpha particles have a mass of 4. You're losing a huge chunk. And because they're so big, they're really weak due to their mass. They can't penetrate your skin. They can't penetrate the walls because they're just too big. So some students are like, well, what's the difference between the alpha particle and the helium particle if I can write it? Honestly, the biggest difference is electrons. And this is the only unit that we really don't really care about the electrons. We're ignoring them. But in actuality, that's the biggest difference. The alpha particle is a nucleus only of the helium atom. There's one that we're leaving out. It's a gamma particle. You can see it on your list of particles, but you don't see it on the list of things that are emitted. Actually, gamma particles are emitted almost all the time, and it's the strongest particle, accompanying most decays. But as you notice, we don't usually write it because it has no mass and it has no charge, and so it doesn't affect any of your numbers. You just have to know it's probably there, and that's the thing that's scary. Because it has no mass, no charge, it can actually get through a lot of tight spaces, like your skin. So when you are decaying a radioactive isotope, even though it might be emitting alpha particles, which are not going to hurt you, it's emitting almost like silent gamma particles as well, and that is the part that we're worried about. So in terms of penetrating power, you have alpha particles, which are huge protons and neutrons that can't even penetrate paper. You have beta particles and positron particles that can penetrate the paper because they're still small, but not that small, but they'll be blocked by wood. And then gamma particles that are so strong because they have no mass and no charge that they can penetrate both the paper and the wood, but might be stuck by things that are really dense like lead or concrete, which is why we use lead suits when we are getting x-rays. So your x-rays are going through your teeth and maybe your face or your ankle if you broke it, but it's not going to go through the rest of your body. We're protecting the rest of the body because of those gamma particles. You can also move where your particles would go. If you have a radioactive source that's emitting alpha particles, the alpha particles will be attracted to a negative plate. So if you hold up a negative plate, the alpha particles will go towards that because they're positive. Beta particles will go towards the positive plate because they're negative, and gamma particles will go straight through because they are not affected by charges since they do not have a charge. You can use a Geiger counter to just basically go through and see if anything's radioactive, and it just records how radioactive something might be. Particles such as ions are detected through film badges as well. It tells us if we have overexposure to any of these particles. Just some things that came up in old exams. A half-life is a time required for half of a sample to decay into a new, more stable element. And this can be used to date old artifacts such as rocks and things that were once living. A long half-life means that the substance stays relatively unchanged for a long period of time, and this is somewhat stable. A short half-lives are unstable elements emitting particles at a regular basis. Calculating half-life comes in a variety of types of examples, so I'm going to go through a bunch of examples to help you understand how to calculate them. But basically, no matter what, after one half-life, 50% or half of your elements present, and after 2, it's always going to be a quarter or 25%. 3 will always be 12.5 or 1/8, and this continues forever. The number will never be 0, so you just keep halving in your calculator. And the half-life times are constant, so nothing actually changed that time. They're printed on table N. So the type of examples you might see is the half-life of radon 222 is 3.8 days. If a basement holds 20 grams of radon, how much will remain after 19 days? So what we would do is divide the times. So to figure out how many half-lives you have, so 19 divided by 3.8 is 5 half-lives. You can only divide times, you don't half the times. You divide times, you half the amounts. So now that I know there's 5 half-lives, I can half my amount 5 times, right? So what we started at 20 grams, we're going to cut that in half 5 times. And so my final is 0.625 grams. Again, divide times, half amounts. The next example, a cylinder contains 5 liters of neon 19. It sits out for 103.2 seconds. What fraction of the sample is still remaining after it's sat out? Determine the number of half-lives. Dividing the time, we gotta look up this one on the reference table since it wasn't given. So 103.2 divided by 17.2 is 6 half-lives. Again, divide your times. And then in order to figure out how much you have left, you're gonna divide your amount by half. We're figuring out a fraction, so I'm gonna start by 1 and count it in half and half and half and half 6 times. So a half of 1 is a half, then a quarter, then an eighth, then a 16th, then a 32, finally a 64th. That's my final answer. The next example says a half-life of technetium-99 using brain tumors is 6 hours. If 10 micrograms are left for 24 hours, how much is administered to the patient originally? So we're going backwards in this example. Again, determine the half-lives that elapsed by dividing the total time by the half-life time. This has not changed. So 24 divided by 6 is 4 half-lives. So if you notice, these last 3 examples always started like that. Divide the times. After you find the times, this time we're going backwards. We know 4 half-lives have already happened, so we're going to start with your ending mass, and instead of halving it, we're going to reverse. We're going to double it. 4 times, because we decided it was 4 times. So 10 times 2 times 2 times 2 times 2 means that we started with 160 micrograms. A laboratory has 400 grams of a sample of phosphorus 32, triggering 400 clicks per minute on the Geiger counter. How many days will it take the phosphorus to decay to only 50 grams and 50 clicks? So we're going to find the number of half-lives that last by dividing your times, right? So dividing your amount by 2. Your amounts always get divided by 2. So 400 divided by 2 gives you 200. We're not quite there yet. Divide that by 200. We're still not there. Divide by 2, you get 50. Oh, that's the question, right? So how many times did you divide by 2? 3 times. Now that you know you went through 3 half-lives, you can look up on table N how long a half-life is and multiply it by 3. So on table N it was 14.3 days, times 3 is 42.9 days. Make sure you always include units in your answers. Here's another type of example. An ancient scroll was discovered with 25% of original C14. How old is the scroll? So again, you're going to start with 100 because that's what your total would be, and half your amount until you get what you want. So a half of 100 is 50. We're not there yet. Half of that is 25. We went through 2 half-lives. Now you can look on table N to figure out how long that would be. On your table, it was 5,730 years. Times 2 is 11,460 years. A radioactive isotope is placed near a Geiger counter and monitored. In 20 hours, the reading went from 500 to 125 counts per minute. How long is the half-life? So we're going to find the number of half-lives elapsed by dividing our original counts in half until your final count. So we had 500, and half is 250, not there yet, and half is 125. So something is a little confusing. That's 2 half-lives. So I don't know how that happened, but sorry. And then if we had 2 half-lives, oh, I see what I did. Haha. No, I don't. Sorry. Okay, so 2 half-lives, and if there was 20 hours divided by 2, that means that there are 10 hours per half-life. So this is not published because it's not something that was on the reference table, so that's why they wanted you to figure it out. One more type. A sample is placed near a Geiger counter, and after 40 days, it's remassed and 25% remains. How long is the isotope's half-life? So this is a similar case. We always start with 100%, and we half it till we get to the amount. So half of 100 is 50, and half of that is 25%. We went through 2 half-lives, and divide the time by those 2 half-lives. So 40 days for 2 half-lives is 20 days per half-life. Now that we're done with half-lives, let's talk about transmutation. So far, we've studied natural transmutation, which means the particle just spontaneously broke down. Somebody had asked about that on the questionnaire. A spontaneous reaction is one where you have one reactant that just breaks down, so one thing before your arrow. So all decay is natural. Artificial transmutation means that you're using some kind of huge apparatus that's making the particles go really fast, around and around and around and around. This is Brookhaven National Lab. So the apparatus is really, really big. The particles are streaming around that circle, and then they hit a nucleus, and it makes that nucleus break up. So that's 2 particles. So if you look at these 2 examples, the first one is a natural transmutation because it has one reactant breaking down. And the second one is artificial because we have a neutron hitting the uranium. So somebody had to be there to do that. So that's artificial because there's 2 reactants. Types of artificial reactions are fission, in which you shoot the neutron at the uranium and it breaks into pieces. Depending on how fast and how hot it is, it can break into all different types of pieces. All you need to know is it breaks. And you need a critical mass in order to do this, so technicians will put in only a certain amount because this is a chain reaction. So once you hit 1 neutron to 1 uranium, that splits it, and then there's more neutrons that come out of that reaction. Those new neutrons will hit more uraniums, they'll split, making more neutrons, hitting more uraniums, splitting, and you can see how this can get out of control. So in order to control it, you only put a certain amount of uranium in. We also have fission reactors. In the fission reactor, if you zoom in, there's control rods that take out some neutrons as it's going, so it's not super crazy. And there's coolant fluid, because anytime you cool something down, it goes slower. Somebody had asked about this, which is the only reason why I have it on my slides. Honestly, really don't talk about this on the Regents. Fusion is the other type of artificial transmutation. This is what happens in the sun. We take 2 hydrogens and we smush them together to form something larger. So in fission, we broke. In fusion, we form. We would love to do this, but here it's very costly, and we just haven't really gotten to the technology to the place that we need it to be. But like I said, it happens in the sun. You take 2 hydrogens and you form helium. In both fission and fusion, you form so crazy amount of energy that we can use it to power things around us, like electricity, instead of using fossil fuels. I want to talk about some other benefits and risks. Some benefits include crops. We use radioactivity to kill bacteria and molds so that we can transport crops. We use it in our smoke detectors to determine if there's smoke in the area because it will disrupt the flow of alpha particles. We can use it to date once living things. We burn it up and we figure out how much carbon that was stable and how much is unstable and how much should have been there that's unstable, because currently you actually have unstable carbon in there. And we can use an apparatus to figure out how much unstable carbon is still left and how long it's been there. We can use it to date rocks. We can use it as tracers to figure out how photosynthesis might work. We can use iodine-131 specifically, like I mentioned before, in thyroid disorders. We take a little tablet. It will highlight the thyroid if there's a problem. So iodine for thyroid. We can use cobalt-60 as a tracer as well. It traces through your brain to see if there's any cancer in your body, to see if there's any cancer. So cobalt-60, cobalt for cancer. Technetium-99 for tumors. So technetium for tumors. And we can use it to for energy around our houses or around the United States. Unfortunately, this can also be a problem because once we break down the particles, they're still radioactive, and so we need places to put them. So although fission is a benefit in that we get energy from it, it's also a risk because we need to know how to store the leftovers, and the storage could be potentially dangerous. One of the biggest places that we store them is Yucca Mountain. That came up on an old exam. And some other things that might have happened is that if we don't store them properly, it can leak into our groundwater, which happened in Canada, and people got sick. We can have meltdowns at our reactors, which happened at 3 Mile Island, Pennsylvania. We can have huge meltdowns that happen in Chernobyl, killing people and killing vegetation and resulting in us having to leave that area and having nobody live there anymore. You can have other things even more recently in Fukushima, Japan, where so much radioactivity was leaked that look at what happened to these beautiful daisies. Other problems are warfare. We use them to kill other people and bombs. So that's pretty crazy. So there's benefits and risks, and you can identify what kind of things would be good and bad for you. An example that came up on a recent exam, as I mentioned, they're going to be towards the end of the section, so you can see them 29 and 30. 29 says, which list of nuclear emissions is arranged in order from greatest penetrating power to least penetrating power? Again, greatest penetrating power means it can get through small, tight holes, so that would be gamma. And least would be things that can't because they're really big, so that would be alpha. I picked number 4. And in number 30, they're showing you a reaction where the neutron is hitting uranium and it's splitting into pieces. Whenever you split something, it's fizzing. Like if you put an alka-seltzer tablet into water, it fizzes and it breaks down. So this is fission, answer number 1. Basically, I went through everything, but I do have some questions. Somebody asked, how do you draw a Lewis dot diagram for bromomethane? I can't draw on the computer I'm using right now, but basically you draw a carbon in the center with 3 single bonds connected to the H's and 1 single bond connected to your bromine with 6 dots around the bromine. That's the best I can do for you. They also asked, in a half-life, what is the uses of the radioisotopes? So we talked about iodine, vitamin 31 being used for thyroids, cobalt used for cancer, technetium used for tumors, uranium used for rocks, carbon used for carbon dating, and that's the only ones I've ever really seen on the exam. And again, fission and fusion differences include fission being that you're breaking down something that's already radioactive, but you're kind of perpetuating it, making it go faster by shooting it with the neutron, so it's breaking, fizzing. Whereas fusion means you're taking small things and you're combining them together. They normally wouldn't want to combine because the protons hate each other and they repel, but you force them together, and that's why they cost so much money to do that, and you have to force them together. But once you do, they form something larger, and it just creates this pretty big ball of energy, actually. So more than what you cost to put in. So it's like the amount of energy you need to put in was an investment, and then you get a huge return of energy. In both fission and fusion, you form a lot of energy, which is, again, a benefit. Fusion actually a little bit more than fission. But again, fission's going from large to small, and fusion's going from small to big. I'm just looking through to see if there's any other questions that I didn't see before. I don't want to see that. There we go. Nope, I don't see anything. So I hope you have a good day and keep studying.